To finish off our chapter on ions, we're going to take a very different tack and talk about bonding in metals. Now, a metal on its own is not an ion, just to make that clear. And we're going to look at metallic bonds, which are bonds within metals, not between bonds of metals and other elements. We're also going to look at an alloy near the end. Be able to describe the sea of electrons model for metals and relate metal bonds to electrical conductivity. So some properties of metal. First off, malleability. You can hammer metal into very, very thin sheets. If you remember Rutherford's experiment, it required a very, very thin sheet of gold. And that's something you can do with gold because it is malleable. There's also ductility. So being ductile means you can hammer something into a wire or you can bend it and it warps like that. It's not brittle, so it doesn't just snap, it really bends and warps. And last, there's electrical conductivity of metals. Basically, if some electrons are put in one side of a metal, electrons will very quickly come out the opposite side of the metals. And this is not true for ions. Yes, ions increase electrical conductivity when put in water or when melted, but trying to use an ionic crystal to move electrons around is just not as efficient as using a metal. So why is metal so electrically conductive? Well, it's the idea of how metal bonds work. Metal bonds are basically how metal ions are attracted to these free-floating electrons. So it's not an issue of a copper atom attracted to a chloride ion, so you don't have two different ions going on, a positive and a negative, which are these electrostatic charges. No, you instead have the electrons kind of floating a little more freely here, and the positive ions engulfed in that. So the whole metal is actually neutrally charged, but there are a lot of free electrons. So you want to think about the valence electrons of metals. They're more free. And if you look at the periodic table, you're going to notice metals are pretty far down, and by the time you're filling in shells for all the different electrons and you get down to metals, you're putting in D shells and F shells, and these are going to allow for a little more ionic freedom, or rather electric freedom. So much so that if you just take a long strip of metal, i.e. a wire, and you just add electrons to one side, i.e. charge, the electrons come out the other side. It's actually different electrons. They just shoot electrons through this sea of electrons, kind of like a wave going through. And this is also going to mean that the ions can move. So metal ions can slide past one another because each individual ion, each little positive charge, is floating in a sea of electrons. If you push some of these positive charges, the positive charges don't go next to each other. They're still insulated from one another by the electrons. And what this means is when you slide metal around, the positives don't go next to each other and they don't break. In ionic compounds, when those positive ions come near each other, they will repel, which will shatter a crystal. So this is how a metal can be ductile or malleable, how you can just slide things around. And if you're thinking metal doesn't sound like it slides well, it's just a lot of force is needed. And if you're thinking about things like gold, though, they can actually be pretty malleable. You can really easily bend gold, which is why most gold rings actually have some other things in them. We're going to get back to that in a few. Now, ions here are in compact and orderly structures, and it's odd to think of metal as crystalline, but metal does have a crystalline structure. Now, remember, in this kind of a crystal, all of these are going to have a same charge. So you're not going to have that coordination number and think about different ions. Rather, you're going to think about how they are packed. So you have hexagonal, face-centric, cubic, or body-centric cubic. And these are the different ways you can put these metal ions in the sea of electrons. You can compare this with ionic crystals. It's a pretty simple comparison. And here, all of the ions are positives surrounded by a sea of electrons. In ionic crystals, they're positives and negatives in a different coordination. Now, an alloy is, think about the gold ring once again. A pure metal of gold is going to be very malleable and very ductile and very easily bent. An alloy is a mixture of two or more elements, including at least one metal. Now, this can include something like iron and carbon, that which we call steel. Having carbon inside of the iron is going to disrupt the crystalline structure, which is going to change its properties. And that will make it harder for these things to slide past each other, and will also make it more difficult for this metal to melt. So it raises the melting temperature, it decreases malleability and ductility. Now, you can actually make steel too brittle by adding the wrong amount of carbon. However, we do see that you can do more than just simply add carbon. There are a whole bunch of things you can add to steel. Your book gives good examples of stainless steel having a little chromium in them. The alloys are often superior to pure metal. Now, in class, we're going to look how bronze is better than copper and how that caused a military revolution, or another example of molybdenum and tungsten used in making better guns.